So next, let's talk about how to estimate the parameters of a lexicalized PCFG. So firstly, I want to emphasize what we've ended up with and why this is going to be a much better parsing model of language than raw PCFGs. And to do this, I've picked an example sentence and an example parse tree with a case of prepositional phrase ambiguity. So the sentence is, the man saw the dog with the telescope, and this is the full parse tree in all its lexicalized glory, where each of these non-terminals has an associated lexical item. So the probability of this tree is again going to be a product of terms with one Q parameter for each rule that has been seen in the tree, and I've listed a few important ones here. There are a few other terms. And so, for example, at the root of the tree, I have S saw goes to NP man, VP saw, and I have parameter Q for that rule, and so on in the tree. So if you recall, if we had been applying just regular PCFGs without lexicalization, we would have had these simple rules such as S goes to NP VP, or VP goes to VP prepositional phrase. And these rules would have had associated probabilities, but as I argued before, these rules are rather insensitive to lexical information. Now we see that these rules actually incorporate rich sources of lexical information, and so take, for example, the rule involving the preposition. So before we had VP goes to VP prepositional phrase, now we have VP saw goes to VP saw PP with. What we see here is that we now have parameters that explicitly model dependencies between lexical items. For example, the dependency between saw and with. And these dependencies are linked to particular grammatical relations. So for example, we have the ability to say how likely is a prepositional phrase with preposition with to modify a verb phrase with head saw. That's basically what this rule is saying. As another example, at the top of the tree, we now have the probability of saw being associated with man in this grammatical relationship where man is basically the subject of saw, and so on through the tree. So you can see how the parameters of our model now have direct access to important lexical information. The challenge, of course, is going to be that we have a very large number of rules and parameters in our model, and so we're going to have to be quite careful about how we estimate them from a set of training examples. So let's now talk how that can be done. This is a model from Eugene Charniak. This is a famous model from the late 90s, one of the first lexicalized PCFG models, and one of the first models to show this very much improved performance over regular PCFGs. So here's one example parameter, which I'll use as an example throughout this section. It's the parameter associated with S saw going to NP man VP saw. So the first step is going to be to actually decompose this into a product of two terms, two parameters, which will make our job slightly simpler. So this first parameter corresponds to the probability. Given that I have S saw, the probability of that rewriting as NP VP. Okay, so if you think we were rewriting S saw, there are many possible ways of rewriting it. Here I have parameter corresponding to just the choice of the rule, and for now ignoring the second lexical item, man, associated with this rule. The second parameter can be interpreted as follows. So say we have S saw, and we've actually chosen this rule. So we've chosen NP VP, and saw is the head of the VP. So I have a 2 under this arrow. Then we have a choice of which lexical item is going to fill in this position in the rule. So potentially any possible word could fall into this position. This parameter is corresponding to the probability that man is chosen in this position within the rule. And these kind of parameters are crucial because they basically model, in this case, the probability for a particular word man to play a particular role, namely the subject of the verb saw. So we see a very direct model of these dependencies between lexical items, saw and man. And again, those dependencies can be very useful for disambiguation. So that's step one. The first step is to take this parameter and actually decompose it into this product of two different terms.